There is a machine right now, tumbling through the dark at 38,000 miles per hour, more than 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes over 22 hours just to reach us from it. That machine is older than the internet. It was built before personal computers existed. Its entire onboard memory is smaller than a single digital photograph on your phone. And yet, Voyager 1 just sent back data that has quietly shaken some of the most confident assumptions in modern astrophysics. This isn't a story about a malfunction. It isn't a story about conspiracy. It is something stranger and more unsettling than either of those things. It is the story of a spacecraft doing something no one programmed it to do, detecting things that don't fit our models, and forcing scientists to confront a question they weren't sure they'd ever have to ask. What is actually out there beyond the edge of our solar system? The mission that was never supposed to last. To understand why what's happening now matters so much, you need to understand what Voyager 1 was designed to do and how small that original ambition was compared to what it became. In the mid-1970s, NASA's engineers realized something extraordinary. The outer planets of our solar system were aligning in a configuration that only occurs once every 176 years. Jupiter, Saturn, Uranus, and Neptune were falling into positions that would allow a single spacecraft to visit multiple planets in sequence, each one's gravity accelerating the probe toward the next. It was a cosmic freeway, open for a limited time only. Voyager 1 launched on September 5, 1977. Its mission was a 5-year planetary flyby. Photographs, magnetic readings, atmospheric data. Go out, collect, transmit back. The spacecraft was never supposed to become history's greatest explorer. It was supposed to be a very sophisticated tourist. But it didn't stop. Voyager 1 kept going. It passed Jupiter and revealed the volcanic surface of Io. It swung around Saturn and sent back astonishing images of the ring system in detail never seen before. And then, rather than slowing or failing, it simply continued outward, into the regions beyond Neptune, into the outer fringes of the solar system, into territory no human instrument had ever entered. For decades, it traveled in relative silence. Instruments failed one by one. Its power slowly drained. The team of scientists and engineers tracking it shrank from hundreds to a small dedicated group. And still, the signal kept coming. Crossing the final frontier. For scientists, one of the most anticipated milestones in Voyager's journey was the moment it would cross the heliopause, the boundary where the sun's influence ends. Inside this boundary, solar wind, the constant stream of charged particles flowing out from the sun, dominates the environment. Beyond it lies true interstellar space, the region between stars, filled with a different kind of material blown out by ancient supernovae and other stellar processes. The models were clear on what this crossing should look like. Solar wind density would drop sharply. Cosmic ray intensity would jump. And critically, the direction of the magnetic field would shift, swinging away from the sun's orientation and aligning instead with the broader galactic magnetic field. In August 2012, Voyager 1 crossed that boundary. And the models were only half right. The solar wind dropped. The cosmic rays surged. But the magnetic field, the one thing that was supposed to clearly announce Voyager's arrival in a new region of space, barely changed direction at all. Scientists were puzzled. Some argued Voyager hadn't truly crossed yet. Others suggested the heliopause was far more complex than predicted, not a clean edge but a tangled, turbulent zone where solar and interstellar forces wrestle with each other in ways our theories hadn't accounted for. That mystery was never fully resolved. And it was only the beginning. The signals that shouldn't exist. In the years since crossing the heliopause, Voyager's plasma wave instrument, one of the few remaining functioning sensors, began picking up something unexpected: low-frequency oscillations. Waves moving through the thin plasma of interstellar space. That in itself wasn't completely surprising. What was surprising was the pattern. The waves weren't random. They weren't noise. They had structure, a rising and falling that repeated with a kind of regularity that caught the attention of researchers. One team described hearing them as a faint hum, a nearly musical resonance embedded in the data. When the audio was reconstructed from the frequency data and made audible, many people who listened to it described an eerie, almost organic quality to the sound. What was causing these waves? The leading scientific explanation involves interstellar disturbances, shock waves, from distant stellar events that travel through the plasma like ripples across a pond. But the timing and character of the waves Voyager detected didn't fully match that picture. They appeared to be localized, originating nearby rather than from deep interstellar distance. There was another detail that made researchers uncomfortable. The frequency of the oscillations had a relationship to the density of plasma Voyager was moving through, as if the medium itself was responding to the spacecraft's presence, as if the act of moving through this space was somehow generating a reply. No one is claiming that's literally true. But no one has fully explained it either. The trajectory anomaly. Then came the movement problem. Tracking the precise position of a spacecraft 15 billion miles away is an extraordinary feat of mathematics and engineering. Scientists use the Doppler shift of Voyager's radio signal, the way its frequency changes as it moves toward or away from Earth, to calculate its velocity and direction with incredible accuracy. And what those calculations showed, quietly at first, then undeniably, was that Voyager 1's path was drifting. Not dramatically. The deviation was subtle. But it was real, and it was persistent, and it couldn't be explained by any known force. There were no planets nearby to exert gravitational pull. The thrusters hadn't fired. Solar radiation pressure, the gentle push of photons from the sun, was far too weak at that distance to account for the change. Engineers ran the simulations over and over. They checked for instrument error. They reviewed the spacecraft's physical condition. What they found was that to replicate the observed trajectory without invoking an unknown external force, the simulations simply didn't work. Something was nudging Voyager. This is not unprecedented territory. A similar phenomenon called the Pioneer anomaly was observed in the Pioneer 10 and 11 spacecraft decades ago. That anomaly was eventually explained by asymmetric thermal radiation, heat leaking from the spacecraft in one direction and providing a tiny but measurable push. Researchers have investigated whether the same explanation applies to Voyager's deviation. The jury is still out. But here is what makes this different from Pioneer. The direction of Voyager's drift is not consistent with a simple thermal explanation. The deviation appears oriented toward a specific region of space rather than simply following the geometry of the spacecraft's own heat signature. That distinction matters enormously. The reorientation event. In the past few years, something else happened that caused a quiet storm in the Voyager science team. Data transmission from Voyager became irregular. Not absent, not corrupted in the usual way aging spacecraft produce garbage signals, but intermittent in a way that suggested the spacecraft's instruments had temporarily shifted their focus. When the data stream normalized, readings indicated that certain sensors had been oriented differently, pointing toward a region not along Voyager's forward path, but back toward the inner solar system. There is a mundane explanation for this. Voyager's onboard computers, running on 1970s technology, occasionally produce errors, memory glitches, timing misfires, unexpected software states. The team has dealt with these issues before and worked around them brilliantly, restoring function to instruments that were essentially being managed remotely with a 22-hour communication delay in each direction. But what made this event unusual was what the sensors recorded during the reorientation window. Energy readings. Particle density fluctuations. Activity in the space behind Voyager, in the region of interstellar space it had already traveled through, that did not match what had been recorded on the way out. Something had changed in Voyager's wake. Whether that change represents a natural phenomenon, perhaps the compression of plasma caused by the spacecraft's decades-long passage, or something else entirely, remains unanswered. What the science actually tells us. Here is where we need to be careful and honest. Voyager 1 has not detected alien life. It has not received a message. There is no confirmed signal of artificial origin buried in its data. The scientists working on this mission are rigorous, careful people who have spent careers distinguishing noise from meaning. What Voyager has done is reveal that the interstellar medium, the space between stars, is far more dynamic, structured, and complex than our models predicted. The plasma waves are real. The magnetic anomalies at the heliopause crossing are real. The trajectory irregularities are real and as yet unexplained. These are documented scientific observations. What they mean is the open question. The universe is under no obligation to be simple. For most of human history, we assumed the deep ocean was barren. We assumed the extreme environments of Earth, volcanic vents, acid lakes, frozen tundra, were lifeless. We were wrong about all of it. Life and complexity have a way of filling the spaces we assume are empty. The interstellar medium is not empty. It carries energy, magnetic structure, chemical compounds, and apparently dynamic behaviors that interact with objects moving through it in ways we are only beginning to measure. Why Voyager still matters. Voyager 1 will go silent in the next few years. Its plutonium power source is approaching the minimum threshold needed to run even a single instrument. When that day comes, it will keep flying, and it will keep carrying the golden record, that extraordinary artifact of human existence, encoded with music, greetings, mathematics, and images of life on Earth, drifting outward forever into the dark. But before it goes quiet, it is still talking, still sending back numbers that challenge our assumptions, still encountering a universe that refuses to behave as neatly as our textbooks describe. The most honest thing we can say about what Voyager 1 has discovered is this. We built something remarkable, sent it to the edge of everything we knew, and it found that the edge was not where we thought it was, and that beyond it, the universe is stranger, more active, and more surprising than our best models predicted. That should not frighten us. It should thrill us. It should remind us that science is not a collection of final answers. It is a conversation with reality. And right now, reality is talking back. We have been sending signals into the cosmos for nearly half a century, and the cosmos, in its quiet, physical, mathematical way, may be responding. Not with language, not with intent, but with the simple, staggering complexity of a universe that is far from finished, surprising us. Voyager 1 turned around and looked back at us. Not because anyone told it to. And what it saw, we are still trying to understand. If this story moves you, subscribe for more deep dives into the mission